continue. Hello, everybody. Welcome to our third seminar of the season. I'm Gina Olivares, and today we're going to have the presentation, the talk of Professor Charles Adam from Durham University. I'm going to leave you to Jose Jimenez. He's going to make the proper introductions. Remember, please turn off your microphones and your cameras so we don't disrupt the session. And if you have questions, please submit it in the chat. So we're gonna be able to ask the questions properly. Jose is gonna do the breaks in order to ask the questions. So please enjoy the talk, and Pepe is all yours.
Okay, well, thank you very much for this opportunity, and thank you very much, Professor Charles Adams, for accepting this invitation. I'll just give a brief introduction of his trajectory in physics. Professor Adams did his PhD in Glasgow University. He says that building probably one of the first single frequency titanium sapphire lasers. Then he did a postdoc in Germany at Constance University, and then he went to the US to study under the supervision of Steve Chu. Later, he moved to Durham University, where he has been the professor for at least 20 years, if I'm correct. And then he tells me that he received the Thomson Medal in 2016 and a Holberg Prize in 2020. His area of research, among several other important contributions, he has made important contributions in Rydberg atoms, in both cold and hot Rydberg atoms. He's very well known in the area of quantum information and atomic physics. So please, Charles, why don't you begin with your talk?
So thanks very much for the kind introduction and also the invitation. I'm very happy to be giving, it's my first seminar of any type in Mexico. Obviously it would be nicer to be with you, but it's also nice to be presenting to you from where I am. And one of the upsides of all this trouble over the last 2 years is we've realized we can do these remote presentations. So I'm very happy to be with you today. So this is an experimental talk, not just because I'm an experimentalist, but because it's using a new type of software that that's been developed just this year. And what it means is you can follow the presentation. So either you can use a QR code reader to read this QR code and it will give you a direct link into the talk. Or in the chat, I copied the web page, which links to my GitHub page where you get the talk. And the reason why I recommend you do that is because I'm going to have some quizzes later. And if you want to have a go at the quiz, then you need to have the link. So hopefully a few of you will have a go and see if you can answer the quiz questions, and we'll see. Hopefully that's going to work, but it's the first time I've done it, so it's very much an experiment. Now, if you want to, you can also, so there's even pens and things. So with this squiggle thing here, you can write on your. But if you want to take notes on the slides, you can do that, and you can erase them again. So this is something interesting that we're trialing out also because we're doing more of these remote online teaching and such things. Okay, so the talk is, it sort of combines some of my interests, which are both research and teaching. So there's a sort of pedagogical. Yeah.
Sorry for interrupting you. They are saying that they have problems with the link. But I copy paste the one that when I click on it, it sends me to the presentation. So can I share that one with everybody? Because it's slightly different. Yeah, okay.
It was the second one that we posted, so.
Yeah, but for some reason they are having problems. Guys, try the one that I just submit on the chat. I'm sorry for interrupting you.
Yeah, that's okay. It would be great if everybody can connect.
Yeah. That's why I think it's. Let me know, guys, in the chat if you can connect. So I'm sorry for the interruption. Keep going, Charles. Thank you.
Okay, great. Yeah, so the title of my talk is Quantum Semiotics, which is a bit unusual. So you probably don't know what that means because it's not something we talk about very often. So I'll explain what it means. And hopefully by the end of the talk, you might understand this picture, which is an example of, well, one example of what we might call quantum semiotics. And it's very much linked into some of the teaching activities I do, as well as the research I'll do, which we'll see as we go through the talk. Okay, so just a little bit about where I am. I can zoom in on these pictures. So this is a population map of England. Here's London, which you may know, and Durham is right up here in the north. And actually, I live out here in the wilds. So this is a picture near where I live, and you can see it's a very sort of wild place. So I'm kind of quite lucky that, well, I like it anyway to live in this wild area where there's very few people. And at the moment, you know, we work a bit more from home, but I'm going increasingly into the laboratory, which is here in Durham. So that's gradually picking up again. Okay, so what kind of things that I do? So my main research area is in experimental quantum optics using atoms. So we're interested in changing the properties of light using atoms in particular. And a big focus of my work has been on Rydberg atoms, so using highly excited atoms. So we excite with lasers the atoms to Rydberg states. And if you're interested in that, we wrote a short sort of review style article on Rydberg physics a few years ago. And our most recent paper, which is about this topic of using Rydberg atoms and light matter interactions in ensembles, cold ensembles, has just appeared very recently in Physical Review Letters. So I'll come to this briefly at the end of the talk. So I'm not going to spend a lot of time going through all the details of that, but it's one of the examples that we're going to build up to during the talk. And something else that's been a big, nice spin-off of our work is the idea that you can also use these Rydberg atoms. So when you excite to Rydberg states, they can, when they decay again, they emit fluorescence. And the type of fluorescence depends on what transitions are made. And you can modify those transitions by shining in other electromagnetic fields, including terahertz fields. So a big activity that we now do is what we call terahertz imaging. So this is an example here of where if you shine a terahertz field that's got some pattern on it into a vapor cell of hot, in this case, cesium atoms, then you see that pattern. So you see the conversion of the terahertz field pattern into an optical pattern. And this has become quite a nice application, applied spin-off of some of the work we've been doing on Rydberg excitations of atoms. Now, the other thing I spend a lot of time doing, like most professors, is teaching. So I'm very keen on teaching, and together with my colleague, Ivan Hughes, who many of you might know, I think he gave one of your talks quite recently. We wrote a textbook on optics, and we also do a lot of undergraduate style experiments, sort of at the cutting edge of undergraduate physics, sort of project-based, and then trying to publish that work. So we try to get our undergraduates to do work that's publishable, like this article in the American Journal of Physics. So what I'm going to try and do in this talk is combine a little bit my interests in teaching and research. So the teaching that I do at the moment, which is very convenient for me because it overlaps with my interests in Rydberg physics and some of the interests in using Rydberg atoms for quantum computing and quantum nonlinear optics, is I currently teach a course on quantum information and computing. And I've been teaching that for some years, but this field is now evolving so quickly that you have to update the course every year, because you probably know now there's a lot of activity in the area of quantum technology. And now there are many companies worldwide, and progress is enormously fast. So we have to keep updating how we go about teaching. And I think there's a lot of new and exciting work appearing in that. And I'm going to cover that to some extent in this talk about the ways we think about quantum mechanics and how that's evolving thanks to this sort of advances in technology that we're seeing very rapidly at the moment. Okay, so as I said, the title is Quantum Semiotics, and the kind of outline of the talk is like what kind of is the problem we're trying to address? What's this semiotics business? What is it in the quantum context? And then I'll give an example which will relate to my own work in Rydberg physics. Okay, so let's think about this quantum computing, and where we usually start when we talk about replacing classical computers with quantum computers is we say what we're going to do is replace bits with qubits or quantum bits. And the difference is that whereas a bit has the state 0 or 1, a quantum bit can be in the state 0 and 1 at the same time. But of course, if we look, then we only see either a 0 and a 1. And we write this 0 and 1 in this form of this superposition. So this is already a very abstract thing that we're writing down here. This state vector for a quantum bit is a very abstract mathematical representation of some kind of reality. And that's what I'm going to touch on in semiotics, is how we use these abstract representations of something in order to simplify the world and understand it. So my first quiz question then that I'm going to ask, and then now we get to test whether this works, whether you managed to connect. So in the previous slide, we saw that I can write down a qubit state vector as a superposition of these states 0 and 1. So the question for you is the amount of information that can be stored in a qubit is one of the following 4. Is it 1 bit, 2 bits, infinite information, or it depends on the measurement? So, and if you vote, then hopefully I see that you're voting. So I can see some people are voting here, except that unfortunately my share screen covers up how many people have voted. I don't know if I can move this thing here. Maybe I can move it. Oh yeah, so I got 4 responses. It's not bad. So let's have a look at what the 4 responses are. Okay, so we've got 1 for 1 bit, 1 for 2 bits, and 2 for infinite. So the good news is that the majority of people are correct. So this is the correct answer, is infinite. And we got 50% getting the right answer. So, and the reason why, if we go back to the question, if I go back to this previous slide here, that these coefficients of the state 0 and 1 are basically they're complex numbers with modulus 1. So they can have any value, and in principle, we can specify them with any precision. So the amount of information stored in these coefficients A and B can be infinite. So the correct answer is infinite. And then I thought, just because this is kind of a strange thing, right? This quantum bit can store infinite information. So I thought I'd just put a little quote from. On the other hand, I think I can safely say that nobody understands quantum mechanics. So I always think it's appropriate to listen to Feynman saying that, because if he doesn't understand it, you always think, what hope for the rest of us? I've got another quiz question. So we saw that the amount of information that can be stored in one of these quantum bits is infinite. So we can ask, what's the amount of information that can be retrieved from a qubit? And again, the answers are the same. So one bit, 2 bits, infinite, but it depends on the measurement. Good, so we got a response. I'm hoping we get 4 again, at least the 4 people that tried before. We got 3. Yep, 4, excellent. I'll just give it a little bit more, seeing if, okay, let's have a look. Oh, so we got 6. Oh, it's still going up. So we got 6. So this is interesting. So the answer is 1 bit, because we either get a 0 or 1. even if we do another measurement, we get 0, 1. We'd have to, if we did many measurements, we could get more information, but on the basis of one measurement, we can only get 1 bit. So congratulations to these 2 people that said 1 bit. So now we have a bit more Feynman.
Don't keep saying to yourself, if you can possibly avoid it, but how could it be like that? Because you get down a drain, you get down into a blind finality of which nobody has yet escaped. Nobody knows how it could be like that.
So I think the point I'd like to make is that already we've got this kind of abstract thing in quantum physics, which is this it's the simplest thing I can think of. It's 2-state quantum mechanics. I can write down this superposition. I can store infinite amounts of information in it, but I can only read out 1 bit of information from it. And it's already strange in a way. And you can say, well, how can it be like that? So I would summarize this quantum semiotics as our way of trying to find a way out of the drain. So we're trying to find some symbolic way or some visualization methodology by which we can gain this understanding that helps us to understand what's bizarre from our classical worldview. So the paradox is then that the qubit stores infinite information, but we can only ever see 1 bit when we make a measurement. And we could summarize that. So my colleague, Nicola Siblich, I've been working with for many years, often says that if you can see it, then it's not quantum. So in a sense, as soon as we make a measurement, we only get 1 bit, and yet there's all this hidden information. So something is very much hidden, but maybe it's not as bizarre as I'm making out. At least at this stage, it's maybe not too bizarre. And I like this picture that I saw the other day where which is a projective measurement in some sense. So this is kind of our object. And when we look at our object, we either see a square or a circle, or if you like, a 0 or 1. But from both of these projections, we don't gain complete information about the object. So this is kind of also about complementarity and wave-particle duality, that we either see a wave or a particle, but we can never see them both at once. So here we either look and see the square or the circle, but we don't see the whole object. But still there's something hidden, there's something more that's hidden. And what's odd is that we can't gain access to this additional hidden thing, at least in one single measurement. So I've got one last quiz. So I think there are already steps in a way that we can start to get more of an understanding of this superposition, which is a little bit like that picture I showed you of the cylinder. So that's a 3-dimensional object, and then we project into some planes which are projecting, if you like, into some states. So if we think of this superposition, so I take this 0 and 1 superposition and I make it a 50-50 superposition, I can ask which of the following, so these are all cutaway pictures of wave functions. So if there are many atomic physicists here, I hope you know a bit about your wave function. So you can say which of the following are superpositions of this form. So 50-50 superpositions of a 0 and 1 state. And this is a slightly more complicated quiz because there's more than one correct answer. So when you're responding, you want to click more than one of these boxes. So let's see this time. So again, we got 6 responses. That's excellent. So maybe we'll have a look. Yeah, so this is good. So this is something like a p state. You know, it's got 2 lobes and it's 0 in the middle. So it would be something like a 2p state, let's say. Similarly, this is also a p state. So these are eigenstates of the hydrogen atom. So I would say these are not superpositions. Similarly, so neither of those are superpositions. So the correct answer, so well done to this person, the correct answer is these 2 here. So the superposition, when I add 2 states together to make a superposition, then I get something that's asymmetric. And in fact, when we take a superposition, we usually get, we induce a dipole. So if we drive something with a laser or a field, we usually induce a dipole moment, which is indicative of this displacement of the charge away from the center. So this non-centric, non-symmetric distribution of electric charge here is very indicative of a superposition state. So now 2 people got the correct answer. So well done to those people. So thank you for participating in the quiz. It was I'm glad it worked. So it was an interesting trial for me. And I also didn't know in some sense, like whether the questions are appropriate or too easy, too hard or something, but I think hopefully you enjoyed it also. Okay, so I'm going to come on to this semiotics. You may not be familiar with the term at all, so I'll define it. And it's actually a very old concept which dates back to John Locke, who was an English philosopher back in the 1600s. And he defines it as the doctrine of signs or symbols. And actually it's very, very common, and we use it all the time in many aspects of life, but we don't think of it so much, we don't refer to it. But you can study semiotics if you want. And so obvious examples are things like the alphabet. So across the world, we have many different types of alphabets, and they all do the same job in that they express language, but they express it with very different symbols and signs. Another good example, and I'm going to use this analogy later, is something like a map. So maps, if we look at maps and we haven't learned how to read a map, then they don't make any sense to us. So if we hadn't learned that blue is a river, and that these lines represent contours and roads are yellow and all these facts about maps, then maps are just like strange images. But we learn how to read maps, and it's kind of similar in quantum semiotics, that the signs and symbols that we use, we have to learn as physicists, and that's what we study. Computing is another good example where it's quite abstract, and there's been interesting ways in which computing has evolved. Now mostly we use letters and numbers in our computer code, but actually early computing was all based on codes written in these punch cards. And there's been interesting work. This is a company called Dynamic Land, where they do all their programming using dots on paper, and then they have a reader that looks down from above at these dots, and they can move dots around on the table and write computer code and do algorithms in this way. So it's a completely sort of interactive way of programming, which is very different to the way we think of it now. And then of course in physics, the main symbols and tools we use are very much sort of mathematical. So we're very used to things like this in the world of physics. But there are not just maths. So I wanted to go back to Leonardo because he was in a way a scientist, but he was a scientist that didn't use mathematics, but he used art as a way of advancing knowledge and understanding. So this is a ray diagram from Leonardo's sketchbooks, and you can see how he was understanding how light reflects off a curved surface and the kind of patterns that we see in our coffee most days, or if the sun shines, which it probably does in Mexico more than it does where I live. Here's another one on shadows, and then Leonardo is actually famous for inventing this gear mechanism, and I think it was his diagrammatic reasoning and his understanding of 3 dimensions that enabled him to come up with devices like this. So I think diagrammatic reasoning is very important, and it's a way maybe we can think about making progress even in quantum. Okay, so let's think a bit more then about what quantum semiotics might be in the context of quantum information and computing. So I've already introduced the concept of a qubit and how we write that down mathematically. And there is a visual representation of the qubit, which is known as the Bloch sphere, which actually predates quantum information. So it was in the work of Bloch and the early work on magnetic resonance imaging, where they were looking at spins. But the same 2-level physics of spin up, spin down, it also applies to qubits, where we just label those states 0 and 1. So basically we write these coefficients in terms of angles. So we have a polar angle and an azimuthal angle. And then the state is completely characterized by now 2 angles. So then we can plot this state as a vector on a unit sphere, or a point on a unit sphere. So this is what's known as the block vector, and it goes from the origin to some arbitrary point, theta and phi, that's defined by these A and B's. And this is correct at least up to some global phase. So there could be another complex number out the front here, but that's not represented. And of course, if we're only interested in the modulus squared of this, then we don't care about any kind of global phase factors out the front. So this block vector picture is very nice. I'm going to show you a few, how it relates back to experiment and some things we can do with it. So when you do quantum computing, what you want to do is you have one of these qubits and you want to control it and you want to change its state. And if in the language of the block vector, you want to rotate the block vector. So you want to make a rotation of this block vector in the block sphere. Now we can nicely relate all the parameters of these angles and the position of the block vector to parameters in the experiment. So if our qubit has two energy levels, which we label as our 0 and 1, so in an atom, they would be the ground state and the excited state, then we apply a laser, which has some amplitude E0, some frequency omega, and then this is detuned from resonance. Then we can basically characterize all these parameters in a rotation matrix that will tell us how this block vector evolves when we shine on this laser. So let me show you some examples of that. So for example, if I choose my laser frequency exactly on resonance, so I have a detuning of 0, and then I choose the phase of the field to be pi/2, then the type of rotation we do in the block sphere is a rotation about the y-axis. So in this picture here, I show the rotation axis in yellow and the block vector in blue. And then I can show you what happens as a function of time. So as we evolve time, then what happens is the block vector rotates around. So if I start in the 0 state, I go to the 1 state. So that would be a not operation. And then I come back to the 0 state. And in the language of atomic physics, or any type of two-level physics, actually, this is known as a Rabi oscillation. So we do Rabi oscillations between 0 and 1. And here I just show one complete Rabi cycle. Now, what's nice here is in this model, I can also include things like decay. So say we were driving an atom and it decays by spontaneous emission. Then when we average over many trajectories, we get, so I go up to this one, and then I can make a decay happen. So there you see now that instead of completing the cycle here, we actually shrink into the block sphere and this block vector gets shorter. So we'll look at that a little bit more later on. So I've always liked this block sphere. I mean, it takes a little bit to learn because it's a bit strange what these different axes represent. And actually it involves complex numbers. So these aren't real world axes. This direction here is in the complex plane. So that's a slight complication. But once you get used to that, it's very nice. And you can describe all this cubic dynamics using the block sphere. And then what's interesting is if you look at what people say in the quantum information and software communities, they don't like the block sphere. So here's an example, and this was from last year. Well, it was just from 2020. So someone says, I don't like the block sphere. It's a limited analogy. And you need to unlearn everything when you do more than one qubit. And so this was a guy who used to work for IBM. He says it's a bad teaching philosophy for quantum computing. This is a qubit. This is how to visualize the state in the block sphere. You need more than one qubit to do anything meaningful. Oops, block spheres don't work. Good luck. Do the maths. You know, so exactly what I've just told you is very bad. It's a bad teaching philosophy. So I want to now look at why is it bad? Why are these people saying it's bad? And what can we do about that? So where do we go next? If we can't use the block sphere, where should we go? You know, where can we, if you want a visualization, some kind of quantum semiotics, then what can we propose to deal with that other than just maths? So firstly, I'll just show you the maths, and then we'll look at how we can try and visualize these states in a way that you may or may not feel is better than the maths. So you could just say, well, I'm happy with the maths. Maths is good enough. Or you could say, no, I want something more. So let's look at an example of like when we go beyond 1 qubit. So this would be, say, we've got 2 atoms now, two level atoms. And then when we write down the general state of 2 qubits, there are 4 terms. So we can have either both atoms in the ground state, one in ground, one in excited, the first in excited and the second in ground, or both atoms excited. And this is how we write the state vector. So as a superposition now of these 4 possibilities. Now, what's strange about this state is we can cross out some of these terms. So we can say, well, let's see if these coefficients can be 0. So there's nothing that says that they can't be 0. So we can get states that look like this, which are a superposition of both atoms being in the ground state and both being in the excited state, or asymmetric superpositions where the first is in ground, second is excited, plus or minus the other way around. And these states, they were recognized as being something a little bit strange, first by Bell. And Bell discussed them in this context of showing that really quantum physics it cannot be reduced to classical. So when I look at states like this, there are correlations built into these states that we can't describe classically. And there's something very odd going on here. So it actually goes way beyond just that we can put all this information and we can't read it all out of 1 qubit. There's something even more strange when we go to more than 1 qubit. And as you probably know, these states are known as entangled states. And once we go to entanglement, it really is something that we can't understand at all from our classical perspective. Now, it becomes increasingly important with the advances in quantum technology that we understand that these states can exist and what we can do with them and how to manipulate them. So it's actually these Bell states that are central to both quantum computing and quantum information. So I've just given an example here. This is really now a very sort of practical technology that we can use, this quantum cryptography. And it's based on Bell states of this type in order to share information using these quantum correlations that's built into these Bell states. So they become extremely important, not just as a theoretical concept, but also in applications, and increasingly so. Okay, so what's sort of the problem here in terms of trying to understand why can't we just represent these entangled states using block spheres? So what we looked at before was we said, I want to do a rotation. So I apply my laser beam or my microwave field to one of these qubits, and I do this rotation of the block vector. And now I want 2 of these qubits. So I just take the block sphere times 2, surely. But that doesn't work. And let's look a little bit at why it doesn't work. So you can, again, write down the mathematics. So I'm now going to do this rotation on 2 qubits, and I write this down as a tensor product. So I do a tensor product of 2 rotation matrices, and I end up with a bigger matrix, which is 4 by 4, and that applies to the 4 terms in this general superposition. And then we can look at what happens if we apply this to a Bell state. So if I choose one of these Bell states, which was the 0, 0 plus 1, 1 Bell state, that I represent as a vector like this with 1s in the first and the last position, or 1 over root 2s in the first and the last position. I apply this rotation. So it's just like we did before. I apply the rotation, and it doesn't matter what angle I rotate by, I always get back exactly the same thing. So something completely different has happened now. Before we could rotate the block vector and it span around. Now I try and do the same thing, but I do it to these 2 qubits that are in this Bell state. I try and rotate their block vectors, and it doesn't rotate. In fact, there's more bizarre things that we can say about the block vector of this Bell state, that it doesn't even have a direction to start with. So it doesn't have a well-defined direction in the block sphere. So if you ask what direction does the block vector point in, you find it points in every direction with equal probability. So it's completely not something that I can reduce to representing using two block spheres. So the block sphere picture no longer works, which is what those people on Twitter were saying about why we have to abandon the block sphere as soon as we go beyond one quantum bit. And I think that's something that is useful to appreciate, actually, especially in experimentalists that we're so familiar maybe with the block sphere picture. Okay, so now I want to introduce something that allows us to go a bit further. And it's just something that we've been working on to try and say, well, how can, I like visualizations. So of course you could just stick with the maths, but I feel I'd like something nice to try and understand the concepts visually in addition to the maths, and hopefully use this diagrammatic reasoning that I talked about in order to maybe in the long run design algorithms. And we're not the only people to be thinking about these kind of topics. There's some very nice work in some various different PhD work in Yale and ICFO. So the criteria that we need in our visualization is that we must be able to visualize any arbitrary multi-qubit state. So it must be scalable, not just to be able to describe 2 qubits, but to describe n qubits. So we want something that can describe any number of qubits, and we need to be able to describe these entangled states. And ideally, we'd like to describe also the process of decay or decoherence, so that we can describe everything. And then once we've got this visualization, we can try and use that to design algorithms or interesting quantum science experiments. And thinking along those lines, it's a bit what the people are now doing in quantum information. So Craig Gigney is a computer scientist, actually, that works for Google. And he's developed this very nice sort of online software called Quark that you can go to with this link that allows you to build quantum circuits. And if you look at that, you'll see that he has many different visualization forms. Some of them are a little bit similar to some of the things I'm going to show you that we've been doing. Okay, so what we settled on as the best thing to work with is the density matrix, which you may be familiar with. Now, the nice thing about the density matrix is it can be used, well, so firstly, it's scalable, so I can use it for one quantum bit or many quantum bits. And secondly, I can also use it to represent this decay process. So decay can be included in this density matrix representation. So this is just the density matrix for a single quantum bit, and it's a 2x2 matrix. And you can relate this very simply back to the block sphere, because these, if I write it in this form, this U, V, and W are the components of the block vector, and they're actually all real. So it's a very nice, simple representation that maps back into our block via. They're the Cartesian components of the block vector. So it relates back very nicely to what we've said already. Now, what you can see is here that each of so the diagonals are real numbers, but the off diagonals are complex. And these off diagonals are often called coherences, and they represent something about the phase of our quantum bit. So the phase term in the superposition states. And because they're complex, we need to use complex numbers to represent this term. And the other thing we can say is that all of these terms have a modulus less than 1. So we have complex numbers with a modulus less than 1. So we can represent all these terms in the density matrix using a complex plane where the maximum amplitude is 1, and we can have any value down to 0. So we're going to do that using a color wheel. So the color represents the phase or angle of the complex number. And the intensity of the color, or the transparency, if you like, represents the amplitude. So that way we can represent all these complex numbers with different colors. Now we have to be a bit careful because of being colorblind, but you can switch your colors if you want to things that work. And I'll also show you that we use some dots to account for that possibility of getting colors mixed up. Okay, so let's now have a look at the type of thing that we did before. So we looked at the block sphere, we did a rotation or a Rabi oscillation and a rotation about this. And now we'll look at this representation using the density matrix. So again, if I advance in time, you see what happens. So I start at the top here. So I start in the 0 state, which is a 1 in this 0, 0 term in the density matrix. And then as I start my Rabi oscillation, you see it starts to populate the other terms. So as I move off axis, these coherences become non-zero. So I start to acquire components in the X and Y directions. And in this case, only in X, because I'm rotating around Y. So these terms always remain real, and you can see they get bigger. And then eventually when I get to the bottom, then my state is all down here. So it's now in the bottom right-hand corner of this density matrix, and almost everything else is 0. And then it comes back. When it comes back, the coherences turn out to be negative. I'm on the negative side now of the block sphere, so it changes to green. And then eventually I come all the way back to 0 again. And if I sort of stop somewhere interesting, right, with a superposition where I've got these off-diagonal coherences, and then I include decay or decoherence, you can see what happens now is this trajectory shrinks down in the block sphere, and what that corresponds to is a decay of these coherences in particular, and you see that they become more and more transparent. So eventually, if I turned up decay enough, these off-diagonal terms would become white because they would go to 0. So essentially what we're doing is just replacing the block sphere with a nice little checkerboard representing the matrix. So a color checkerboard to represent this density matrix. And then you can do, for example, any rotation. So this is a rotation around X. I'm just including it to show you, well, you get different colors because here we're rotating in the around X. So we go in the direction of Y, and the Y terms have an eye on them. So you move in a different plane in the complex plane. So you get these yellows and purples because you're moving in this color wheel in a different direction. Okay, and then here's one with doing a rotation around. So here I start with a superposition state. So everything is uniform. So everything starts as a 1/√2, and in the density matrix, all these terms are a half. And then in time, we do an evolution in time around the x-axis, and you see it's just the coherences that change here. So they change color as we do that. And then if we increase decay, so this is what I would call a T2 time. So we're decohering the coherences, or if you like, dephasing or and you see there's this decay of the off-diagonal terms. So the whole thing shrinks towards the axis. And eventually when we make this T2 time very short, which is over in this position, then we decay very rapidly and these off-diagonal terms disappear. So everything that we might do in the block sphere, we can do with this color checkerboard density matrix representation. Now it starts to become useful when we go beyond 1 qubit, because that's where the block sphere broke down. So let's look at now the case of a Bell state. So now we have 4 terms in the density matrix. So remember, the superposition had 4 components. So when we represent the density matrix, it's a 4 vector times a 4 column vector times a 4 row vector. So we get 4 by 4 matrix and 16 terms. And if I start out in the Bell state, that gives me some 0, 0 and 1, 1. And then I get these coherences in the off diagonals here. So that was like the superposition state, but now it's in these corners for this particular, starting in this Bell state. And now we can evolve in time. And it's very dull because, as I showed you before, when I apply this, this RY rotation, nothing happens. So, but maybe you don't believe me that anything's happening because nothing's changing. So we'd better look at a different case. Well, this is a summary of all different input states. So if we'd have taken just, let me just go back to that one, and I'll just show you, if I take the initial state here and I do the time evolution, then you see something does happen. And if I take the opposite initial state, so everything in the 1, 1 state initially, you'll see that everything goes to 0, 0 with time. So now I'm in 0, 0, and then I come back to 1, 1. So those 2 cases, something happens. So you can believe that something happens. And it's only when I go to this Bell state in between that I see that nothing happens. So you see nothing happens now. So that's this irrotationality of the Bell state that we mentioned, because the Bell state has no direction anyway. When we try to rotate it, it can't rotate. And that's summarized in this sequence here. So we take a set of different initial states, different superpositions. So there are 5 different initial states, and then this axis represents time. So the initial state 0, 0 evolves to 1, 1, and then back to 0, 0. Similarly, 1, 1 evolves to 0, 0, and then back to 1, 1. Whereas I take the Bell state, which is the middle case, then we see that it doesn't change. So this is irrotational. So in this picture, we can see these interesting properties of the Bell state popping out of the dynamics just by in a pictorial way, which personally I find quite useful. Now, once you've set up this framework to do this, you can start to study other cases. So if instead of an RY rotation, you try to rotate around the x-axis, so this is just changing the phase of the field, then something very different happens. So again, if we start with the Bell state, which is the superposition of 0, 0, and 1, 1, and now we look at what happens in time, it's actually completely different. So you see now you go, so we start with these, all the corners red, and then in the middle, we end up with this state where all the central region is green. And if you work out what's going on here, then what you find is that you've gone from 0, 0 to 0, 1 plus 1, 0. So all the central area colored is this state 0, 1 plus 1, 0, which is another Bell state. So actually for the RY rotation, we do see some dynamics when we apply it to both qubits. But they're different, and it's actually an oscillation between these 2 Bell states. And actually, I didn't know that until I wrote the codes to make these pictures. So I learned something new by looking at this. And then if we keep the time evolution going, then we come back to where we started. So once you've got these pictures, you start to see things happening, and then you can relate that back to the maths to try and understand why does it look like that. Okay, so this is the type of methodology that we've been developing to try and understand some of what happens in the dynamics of entangled states. So now I want to show you an example that very much relates to experiments and relates to some of the work we do in Durham using Rydberg atoms. And the example I want to mention is known as a Rydberg blockade. And the idea is that we try to drive Rabi oscillations on 2-level atoms, but the upper level now is one of these highly excited Rydberg levels. And the interesting property about these Rydberg levels, when atoms are in these Rydberg levels, is they become very strongly interacting, and that interaction shifts the energy level. So I'll show you this a bit more in the next slide. But this is a very nice recent experiment from Manuel Ender's group in the US. It was just published last year, and they use optical tweezers to make pairs of atoms. And if the atoms are very well spaced, then you drive these Rabi oscillations between the states 0 and 1, if you like, and you see nice Rabi oscillations, but of course they decay because of the decay and decoherence effects that we've seen. So, but at least initially we see these very, very nice Rabi oscillations just going essentially between the states 0 and 1. So this is the probability to be in 1. Make that bigger. Now, what's interesting is what happens when you put these atoms very close together. So here the atoms are spaced by some greater than 10 microns, and now we put the atoms less than a few microns apart. And you see the Rabi oscillations really change in frequency is the main result. And also what they're measuring now is a different probability. So rather than measuring just the probability to be in the excited state, they measure 1 minus the probability to have a superposition of 0 and 1. So 1 atom in 0 and 1 atom in 1. And you see the Rabi oscillations to this state are now faster than those. So I want to explain how that comes about and then trying to visualize that using our semiotics method. So the basic idea then is we have these 2 atoms here that are represented by this these purple dots, and these 2 atoms are separated by a distance r, and we try to drive them both to some Rydberg state. But first, if we just consider what happens if one is in this Rydberg state and we try to bring the second one to the Rydberg state. Now, if they didn't interact because they're very far away, we could easily do that. So the energy to excite the second one would be the same as the energy that we needed to excite the first. So it'd just be this energy level spacing. But now, because the atoms interact, they have these enormously strong interactions. When the two atoms are closer than a certain distance, then the resonance is shifted very, very far off resonance. So now the second atom can't be excited, and this we refer to as blockade. And this blockade happens when the shift due to these van der Waals interactions between the Rydberg atoms becomes larger than the line width to excite them. And that defines what's known as the blockade radius. So when we bring the two atoms less than a few microns apart, then we're in this blockade regime where we can only excite one atom within this distance known as the blockade distance. Now we can look at what happens in terms of dynamics by writing down a Hamiltonian for this driving. So this is my Hamiltonian to try and drive my two atoms to the Rydberg state with some Rabi frequency omega. And then I include this shift, this van der Waals shift for the doubly excited Rydberg state. So this is the shift in this bottom term here. And this blockade occurs when this shift is larger than the Rabi frequency. Now you can do some theory to work out what's going to happen here. And what we do theoretically is it's convenient to make a basis change. So you basically change from these states, if you like 0, 1, 0, 0, 0, 1, and so on, or in this case 0R and R0, you look at these superposition states, which are like the Bell states. So they're symmetric or anti-symmetric Bell states, these phi plus and minus states. And if we change into this basis, then the matrix gets a little bit simpler. And what we find is that we can drive, so this is the picture that kind of summarizes that we have our two atoms in the ground state. We're trying to drive them to this Rydberg state, but we can't get up to the doubly excited Rydberg state because of this blockade effect. So what happens actually is we end up going to a superposition state, which is a superposition of one atom still being in the ground state and the other atom being in the Rydberg state, or the other way around. And this is one of these Bell states known as phi plus. So what's interesting in this Rydberg case is this entanglement, this Bell state just emerges immediately and directly. And I always found that amazing when I first learned this piece of physics, because I always thought entanglement was so bizarre and must be so difficult to observe. And yet all we need now is two atoms nearby one another, and it's not even that close, so they can be a few microns apart, like 4 microns apart, and then I drive them with just one laser, but I try to drive them to a Rydberg state, and rather than getting that, what I get is this bizarre Bell state, which, as I've shown you, has these very strange irrotational properties. Now, the other thing I learned from this piece of maths is that the Rabi frequency to go from this ground state to the Bell state is √2 larger than the Rabi frequency to just drive one atom on its own. So we get this speed up process. And in fact, if you go to n atoms, you get a √n out the front. So the dynamics goes quicker, which is also a very interesting property of this system and can be useful in some contexts. Okay, so let's have a look at that then using our density matrix picture. So it's the same as before now. I have two atoms, so I have a 4x4 matrix with all these 4 possibilities. And we start in the 0, 0 state, which is a red square here. And then if I just drive this system with no interaction first, so we've got the interaction 0 at the moment, and then as a function of time, we see what we saw before. So basically the population goes over to the, keep moving this along. So it goes over to the excited state, 1, 1 or RR in this case, when we're talking about Rydberg atoms. And then we come back again, and you see as on the way back down, we see green because it's coming down on the other side, if you like. So that's all very simple dynamics, and we understand what's going on there. And then we turn on a bit of interaction, and then it starts to go different. So firstly, you see different colors emerging. So you see already it gets very complicated, and you see completely different dynamics now that you have this interaction. And if you actually watch these little circles here, they show you the trajectory that you go in terms of the complex plane of these individual terms. So whereas before we just saw it moving out, but now if you look at this 1-1 state, it actually does a strange little circle in the complex plane. So it's a completely different kind of dynamics to what we saw before, just by adding interactions in here. Now, as we crank up the interaction, you can start to see now that we get less and less in this doubly excited Rydberg state. So the blockade starts to kick in. So at the moment, we've got the interactions 3 times the Rabi frequency, but to completely suppress this, we need the interaction to be much stronger than the Rabi frequency. So if I keep cranking up the Rabi frequency, then you can see that we start to completely suppress this excitation over here. So if I go to the extreme case, so now if I've got interactions 15 times the Rabi frequency, then you see that what happens is I can't get to this doubly excited Rydberg state at all anymore. So I go all the way across, and I never excite the doubly excited state. And you also see that if I go to this point there, stop it around here, then you see now this is the Bell state, 0, 1 plus 1, 0, with all these terms red in the middle here. And we can also see the speed up, because you'll see that if I look at when do I get back to the start, so it's about, that's the closest I can get to the start. You'll see that it's now the omega times time over 2 pi is about 0.7 when I get back to the beginning. Whereas when I had no interaction to get back to the start, I had to do 2 pi. I had to do a full oscillation, full rotation around the Bloch sphere. Whereas when I have when I have strong interactions, this oscillation is computed in around 0.7, which of course is the √2. So we see the speed up in this dynamics. So the picture I showed you right at the beginning of the talk was basically a summary of that. So this is just a big matrix showing all of these density matrix for the different cases. So this is the no interaction case. And then as we move down here, we always start with the same initial state, but now we're increasing this interaction, the van der Waals interaction, by bringing the atoms closer together. And then you see that this state here, this guy here, is completely suppressed. So we can't get the RR at all. And we also see this speed up. So we see that we return to the initial state by this column, which is about 0.7 of the complete cycle. So before it took us 2 pi, and now we complete our Rabi oscillation to the Bell state in 0.7 of that time. So I like this picture a lot. I think it looks nice, as well as just telling us a lot about the physics. And it's got all the physics of blockade in this nice visual representation. Now, once you have this methodology, so I'm not really a quantum algorithm person, but once you've built up a way of writing the code and visualizing these density matrix, then you can go wild. And this is an algorithm known as the quantum Fourier transform. Now, I like Fourier transforms, so I should like quantum Fourier transforms. And it's a whole sequence of gates, in this case applied to 4 qubits. And if you visualize that using the same method, so this is just 4 different initial states as our input, and then we look at each stage of this quantum Fourier transform and what patterns you get. And I think this is an example where I would come back to maps. So just like when we learn how to read maps, we have to learn how to read these pictures. So it becomes almost an image recognition type of task that in order to understand what's going on, they just look like crazy patterns. But once you become more familiar, you can start to pick out from those patterns what the dynamics is and why it might be interesting. Okay, so I hope I've just got a little bit of time to try and relate this to our most recent work on using Rydberg blockade. So in our experiments, we have cold atoms and we shine in lasers and we try to excite Rydberg states. And we exploit this blockade process that I've shown you. So I've shown it you just for 2 atoms where we try to excite 2 atoms, but we have n atoms. But again, the same blockade applies, and we can only excite 1 Rydberg excitation within this blockade radius. So we shine in light and we only create 1 excitation, and that 1 excitation is shared amongst all n atoms in this case. Now, what's nice about that is we can store 1 excitation in our cold atom cloud. So there's just 1 excitation there, and then we can read it out again. So we can now de-excite this single excitation, and it comes out and it produces, because it's only 1 excitation, it produces exactly 1 photon. So this blockade process is a nice way of making a single photon source. And this picture here shows what we can measure in our dynamics. So we send in a pulse of light, which is just classical light actually, and classical light is made up of a superposition of different numbers of photons. So we might have 1 photon, 2 photons, or many photons. And that classical light, when you look at the coincidence counts so how often do I get 2 photons, and you normalize that, you always find that you get what's known as this G2 number. So the normalized coincidences is just 1, and that's the property of classical light. But if we if we send the light through our Rydberg cloud, because of this blockade process, everything changes quite dramatically. So if we just look at the dynamics and turn off the probe field and then measure the light that's coming out, we first see what's known as bunch light. So over on the right here is this G2 parameters that measures whether I get more 2 photons or less, lots of 2 photons. So initially we see what's known as bunch light, actually loads of photons coming out together. And then a short time later, we see what's known as anti-bunch light. So suddenly this coincidence switches from having more than we would expect for classical light to less than we would expect. And then it comes back up again towards 1. So we see this bunching and then anti-bunching. And this is a property of this blockade process that gives us initially fast readout of many photons, such that there's only 1 left. And then in this little bump here, we see just the final single photon released. So at this moment here, we have a very nice single photon source from our cloud. So our single blockaded excitation becomes a single photon readout. And the experiments that we've been doing in this recent paper is we store this single photon in a Rydberg state, and then we use a microwave field, and then we do some of the things I've been talking about, but now using microwaves rather than laser fields to drive these Rabi oscillations, to perform rotations in the Bloch sphere. And because we just have 1 excitation in our cloud, 1 photon, we essentially have a single qubit. It's a strange qubit, and we call it a collective qubit because this excitation is shared amongst n atoms, but we can think of this as a single qubit, and we can now drive Rabi oscillations of this single qubit. And here's an example of the type of data or type of experiments that we do. This is known as a Ramsey type experiment, where we drive our qubit into a superposition, and then we wait a while, and then we apply another pulse to read out the relative phase of that superposition relative to our field. And we see these nice oscillations known as Ramsey fringes on this stored photon. And if we change the parameters slightly, we can change the envelope of these Ramsey fringes. So basically using blockade, we can start with many photons and many atoms, but isolate a single photon and still have many atoms, but we have a system that behaves like a single qubit, even in this many atom system. So I think that's kind of a nice application of blockade physics and some of the things I've been telling you about earlier. Okay, so that brings me to the end of the talk. I hope that I'm about right on time. So I was maybe over-ambitious. I don't know how well it's worked, but trying to combine a bit of research, current sort of advances in knowledge across a number of fields, including quantum information and experiments on Rydberg atoms. But some of the points I want to make about is in order to understand this and to get around Feynman's thing, but how can it be like that? Or don't worry. I think we should worry, and we should think of better ways of trying to visualize quantum mechanics. So that's my kind of appeal to all of you to think about, can we do a better job and really address and not be stuck in this hole that Feynman talked about. I think the density matrix is a good way because it has all this information. It's nicely scalable. It also includes the dephasing, decoherence, decay, and such on. Now, in terms of extending this, where might we go? So I showed you these complicated patterns when we look at larger numbers of atoms or qubits. And I think the interesting question is, the question that interests me is can we turn this kind of task, or can we turn quantum algorithms and quantum simulation into some kind of image recognition task? And then can we close this loop between quantum computing, image recognition, machine learning, and artificial intelligence, so that we basically we use our computers to both do the simulation, but to recognize the answer and to make some progress in things like artificial intelligence and designing new medicines, for example. I guess that's the hope for the future. So on that note, I'll finish. I think there's just like to acknowledge my collaborator, Nicholas Sibelich, in particular because he's developed all this software that I'm using with these nice interactive plots where you can do wonderful things in sliders. And I think these are a great sort of pedagogical tool for teaching. And also he's developed this, the presentation software that I'm using that allows quizzes, and also the annotations that I've shown you at the beginning is known as Caroline. And if you're interested in adopting this rather than PowerPoint, then you can already download that from GitHub. Okay, so I'll finish there. Thanks very much.
Well, thank you very much for this wonderful talk. There is at least one comment here from Eduardo. And he asks, Eduardo Gomez from San Luis Potosí, he says, nice visualization, thanks. Changing the base of the density matrix changes the pattern. Any wisdom on a clever choice of a base?
Yeah, if we choose a different base, it's like, I guess what you're thinking about is, could we go from like a 0-1 basis into a plus-minus basis? I think that's an interesting question, because you might say, okay, I want to rotate my basis, and then I would look at how the image changed or the pattern changed, and then decide on the most appropriate basis for whatever it is that I want to try and solve. So even the basis rotation might become a tool in the sort of pattern recognition way. So I can feed back to the image and then use that as a methodology to solve the algorithm, if you like. Okay.
Carlos Pineda has a question. Can we unmute him, or?
Yeah, I already did. Carlos, you
Okay.
have you can talk now.
Okay, so thank you very much for the talk. I also appreciate very much the visualization tools, because I think that they teach us physics simply. Regarding this phenomenon of the blockade barrier, Rydberg barrier, I could understand a little bit more with the pictures that you showed. That could get some intuition. However, with the Fourier transform, they delivered like nice pictures. However, I am curious about what you learned from those pictures.
Oh yeah, yeah. So if I show that again, yeah, I wanted to do this example simply because I wondered what it looked like. So all the examples I'd done were only 2 qubits, and I was thinking, okay, I need to do something with a few more to see what happens but I'm not sure whether at the moment I look at this and say anything nicer than, well, the patterns are interesting. The only other thing I learn is, well, how shockingly different it becomes depending on what initial state I put in. So, but at the moment I can't follow. So I would say that in some sense, I don't have a real intuition of this quantum Fourier transform. You know, I've kind of read about it and you can sort of follow the mathematical description, but I don't have a feel like I have a feel for normal Fourier transform. So, I mean, we're familiar in optics, if we do optics, about how the Fourier transform works. And I have a real sense that I have a feel for Fourier transforms, you know, and about breaking up square waves into waves. But somehow the quantum Fourier transform, it's complete mystery for me. So I thought maybe if I make these pictures, it'll all start to make sense. But I'm still at the stage where, okay, I made the picture and it still doesn't make any sense. So I'm sorry, but maybe I need to do a bit more work on it.
Any other questions?
You can raise your hands. Well, the digital hands, so I cannot mute you if you want to do to ask the question, guys. Anybody?
There is
Comments?
okay.
No, it's just Carlos saying thanks.
Right.
Eduardo, okay, let me, Eduardo.
Hi, I have another observation. From the image that you show of the 2x2, the two particle system, it almost looked like you started from a corner and there was a wave propagating through the other side, kind of like an optics propagation problem. Have you thought about that? If this can be cast into just a wave propagation problem, meaning that the entries are just like a medium, and then whenever you add the potential, like the column blockade, you're changing like the index of refraction of the medium, and that's why it doesn't go there. There's an interface.
I think it's a very interesting idea, and what would be nice would be to extend the blockade picture to more qubits. And so if you go, so I think this wave propagation, it looks even nicer when you go beyond 2. So you see the sort of flow from you know, it's essentially what we would call the Dickey ladder. So we would go from sort of the bottom of the Dickey ladder up to the top of the Dickey ladder, and it looks like a wave propagating through this square. And then by like you say, by you put in obstacles with blockade and interactions, you sort of put in boundary conditions that apply new conditions to this wave. So I think it's a very interesting, I like your idea that maybe we can think of it as a wave propagation effect, and we start to see how that kind of emerges, and there are analogies with optics or other types of, because clearly all of quantum is waves. So that I think the key to the visualization is to map that onto sort of wave concepts that we're familiar with in other contexts, and then say, oh, we understand this because we know now it looks a bit like water waves or waves in a solid or something, or waves on a lattice. Yeah, so yeah, I like that idea.
Thanks.
More questions?
Raise your hand or let me know in the chat if you want to make a comment or ask a question, guys. This is your last chance. Nope. Apparently, no, nobody. Well, that's it, guys. Sure. Yeah, apparently it is. So thank you so much, Pepe and Charles, for accepting our invitation to this seminar. It was very, very interesting. And as everybody's saying, the visualizations are amazing. And actually, I don't know how many people answered the quiz. So I hope, guys, that you felt very, very well about answering the quiz. It was very, it was a different dynamics in our seminars. Thank you so much. I don't know if you want to add something else, Jose. A lot of people is congratulating you. Sorry, Pepe. they are congratulating you, Charles, Alejandro Fonseca, and Asaf. Thank you so much, and excellent talk, they say. So yes, Pepe, I leave you the microphone.
Well, thanks again. And you mentioned at the beginning that this is your first talk for Mexican audience, but we will make sure that it is definitely not the last.
Good. Yeah.
So we will hope to hear from you some more.
Somebody's asking if there is a prize if they answer right.
Oh, next time. The thing is, I don't know who got it right, so everybody can claim they were the ones with the correct. So I wonder for people that, so there was about 6 or 7, but there seems to be maybe about 30, 35 people. So, but maybe people couldn't connect. I don't know, or maybe they just.
I believe they were shy.
They're just shy with the
questions. Yeah, they believe that probably that their names were gonna appear, and they didn't want to. Yeah.
No, maybe I should emphasize it's all anonymous, so I didn't know who was who, but yeah.
At the beginning, it took me a while to find out that I was using the pen mode, and I had to go back to the other, so it wasn't quite clear.
Right, how, yeah. So there's a few tricks with getting used to the software, yeah.
But I mean, if I may suggest, probably the prize would be a nice tile. I mean, a nice quantum tile.
Yeah.
Of, say, the Fourier transform, the quantum Fourier.
Yeah, or a T-shirt, maybe.
Right.
Yeah.
Yeah, we can print them. Yes.
Yeah.
So thank you so much, Charles.
Thank you.
Really nice to meet you. You were very, very nice. Thank you, Jose, for helping me with the moderation of the talk. And thank you everybody out there for connecting and sharing the seminar. I hope to see you in 15 days. It's not gonna be a seminar next week, but until the second week. So you are also invited, Charles, if you want. I can send you the invitation to attend. Thank you so much, guys. Have a good day. Have a good weekend.
Bye. Bye, everyone.
Bye-bye.
Bye-bye, guys. Thank you.